So here we have the final expression from the last video, and now we want to do only one last thing, and that is to express this integral in these variables t1, t2, no, t3, t1, t2, which denote the intervals between the action of the superoperators v. So nothing else we will do here than just a substitution for what t with tau, tau dash and tau 2 dashes, and this will go into t3, t2 and t1. Okay, this is not going to make anything strange. One thing which we will do in addition to this, in order to have our expressions actually formally more simple at the end, is that we will shift this initial time t0 to minus infinity. The minus infinity is a time where we are safely before all pulses arrive. So originally all the lower bounds of the integrals were minus infinity, and now after this substitution they will end up all in the upper part. For example, we will have t minus t0 in the first integral of t3, and this thing, because it's minus infinity, is plus infinity, and we will write all the integrals at the end in this form. So we will have integral to the infinity over dt3. So let's now rewrite our third order polarization with the substitution. So we will get integral from 0 to infinity dt3, integral from 0 to infinity dt2, integral from 0 to infinity dt1. I recommend to everybody to make this substitution for themselves, just to practice a bit. So then we have the consecutive interaction of the system with light, rho equilibrium here, and all the dependence on this external time t will now go into the field. So here we would have t minus t3, t minus t3 minus t2, and e to the power of e with the argument t minus t3 minus t2 minus t1. Because these are delays, we can see that this will be the field that acts as the last. So this one will be the sort of latest, the earliest or deepest back into the history. So out of here we can already define, and we forgot I to the power to the I to the third power. Out of this we can already define third order response function as a function of t3, t2 and t1. That is equal I to the third power. Now we would occasionally also like to well, it would be nicer to have these integrals from minus infinity to infinity, for example, for some reason of Fourier transform or something like that formally. So we also insert Heaviside step functions here in t3, t1 and t2. Now t2 and t1, and only after them we have this trace over mu u t3 v u t2 v u t1 v rho equilibrium and close. So this is the response function, and with that response function, we are repeating several times basically the same equations, but with that thing we can write the p3 as p3t as an integral of minus infinity to infinity dt3, dt2, dt1, response function of the third order t3, t2, t1, and e to the power of t minus t3, e to the power of t minus t3 minus t2, and e to the power of minus t3 minus t1, no, t2 minus t1. So this is the final expression that we have, which relates the polarization with the electric fields through something that we will be later able to calculate out of some microscopic theory of the molecules in our sample. So see you in the next video.